Now making titration plots. So from experiment, we can trace the history, right? Potential versus volume of the titrant added. Then you get a curve like this. Then you use a ruler to draw the best straight line, overlap the curve like that, the maximum overlap. So the best overlap is going to give you uncertainty, right? Because there's a distance right here. So you move your ruler, there will be an uncertainty over this entire region, so this region. So it's rather long. So now if you plot the first, so-called the first derivative, is delta E over delta V versus the volume, then you're going to get data point here, data point here, data point here, data point, data point, something like that, and then you connect and follow the trend. Follow the trend, extrapolate. So the dotted lines represent extrapolation. Then because the origins are two opposite sides, so it's going to meet at a point. So now once it meets at a point, then you're going to call that the endpoint volume. Rather than, when you crooked the line, then you can call this endpoint or that endpoint, or, it's more difficult. So here you have a more accurate extrapolation. So this is the first derivative plot. Okay, so going to minimize the plus minus. But now there's still a distance from here to here, right? It would be nice the distance is shortened, then your endpoint detection would be even more accurate. And therefore, why not do second derivative plot, okay, to reduce the extrapolation. Okay, so that is the second derivative. So you do the delta of the delta, what it amounts to. Okay, then you're going to have data point here, then connect, and then here, then you connect, and then here and here. So you're going to meet at the tip. You don't use the negative value, but only the positive value. So where they meet, then that is the endpoint. So the reason now is the extrapolation distance is reduced. So this experiment we are completing today, you're going to make a lot of titration plots. All three types will be included. So let's talk about that later, a little bit at a time. You don't want to have so much information to make you less interested in doing the experiment. So I make it seem to be easy, so you can enjoy more. Okay, in terms of calculation, how do you get the delta, and delta, right? All that. So do this manually. If you were to do this manually, but no point to do that, right? You have Excel. So you can use Excel to do the calculation. Dr. Salmer's website has a great detailed layout on Excel and tell you how to make the plot. So the idea behind it is, so you add a volume of titrant. Then you measure the potential. Okay, then you add another volume, then you measure the potential. Volume, measure the potential, volume, measure the potential. So here, what you have done is you intentionally to make the increments to be 0.05 different to make the calculation easier. Although it doesn't have to be, okay? So now you have the two columns. Then follow the delta. Delta means difference, right? Delta E is corresponding to the difference between those two. So that is delta E. So now you get a volume, this volume. Then you have a delta E. Okay. Then here, then you have this delta E, this and that corresponding, and you have delta E. Then a delta V, the delta V is the difference between the two volumes, okay? So the increment, right? So you have this volume, that volume, so increments represent 0.05. So everyone is 0.05 in this case. Then straightforward now, delta E over delta V. So delta E over delta V is equal to that, so on and so forth. Okay, and now here, the difference between delta E, right, that is delta squared E, so the difference between the two delta E. So here is delta E, so the delta between those two is equal to that, so on and so forth. Then, so on and so forth. So then you make plots. So then this is direct, then the delta E, delta V over the V average of the two. Okay, and so on and so forth. Do I have any more? So be sure to check that out. Then just a matter of numbers. Okay. Now there's a so-called Green's plot, because he came up with this idea, mathematical transformation, to see the endpoint. So your analyte is going to be in solution. Your titrant is going to be in solution as well, right? So look at the situation. So your analyte will be, initially your analyte is 100%. Then during titration, then you're going to less and less and less. At the end point, you have 0 of the analyte. So it's going to follow this. Okay, then as long as I trace the trend of the potential, then I can extrapolate to meet 0 to get the endpoint. So that's the idea, right? You don't have to exactly go to 0 and catch that. That's my endpoint, right? Rather, grant the sky is just follow the potential here, then extrapolate to 0. Okay? So that involves the extrapolation. Now, oppositely, you can do the same thing. So at first, you have 0, okay, during your titration until you meet the reach the endpoint. Beyond the endpoint, and you're going to have more and more potential belonging to that, so you can extrapolate to the quantity of 0 to determine that endpoint. Okay, while Grant is going to follow this way. This way is easier. So actually, this way, then you go lower and lower, and then this way, then you go higher and higher. So both of them is going to meet that 0. So going to be extrapolate 0. Then you monitor another one. Then it's going to be extrapolate like this. This is titrant. This is analyte. Okay. So this is 0. That is your endpoint. Now looking at this case here. Let's say this is your titration, the example. So you use a silver wire electrode, okay, a reference electrode. So you're going to measure based on this half reaction. So this half reaction is going to give you an E naught. So the E experimental, the Nernst equation again, E observed is equal to this. Subtract the reference electrode, right? So that's what we learned. So this is the indication electrode. Okay, so now do the math here. If we extract the log of analyte, okay, log analyte, then is equal to minus 16.9 multiply the E observed plus the constant. The constant is going to be equal to this one, subtract that over that. Okay? So you take the picture and then try to figure out where the 16.9 come from. Okay? Because of this guy, the reciprocal of that. And John?
Where did you get that 0.059 number from?
Funny, very funny. And the one as well. I like and John. Okay? That's good. So now, therefore, the concentration of that is equal to anti-log of this whole deal, right? So now you have something to plot against each other.
Think of every minute, aren't you?
Okay. Now, the chloride concentration, the history of chloride concentration in your titration is you to think of it standardization. Okay? So you have MV chloride. So we are talking about the concentration remain behind. Okay? So MV minus the titrate added, right? That's how much left behind, right? 1-to-1 coefficient in this case. That is how much is left behind, and then correspondingly, the volume plus the volume of the titrant. So at any point, this is true, right? During the titration, at any point, that's true. So rearrange to that the previous relationship, then is equal to this multiply the chloride concentration. The chloride concentration is equal to this deal here. Okay, so now the big circle. Then this big circle is the parameter we're going to use for the y. So this multiply the anti-log of this is equal to that. So just lazy, then plug in the whole circle thing, etc. In here versus the volume of silver added. Okay, so your Excel is going to be able to calculate the volume. Whatever you have added, volume of that, change simultaneously, and then when you read your potential, then this is a quantity, and this is a constant. And therefore, now you have a reading here after adding so many titrant, a reading here, then you can extrapolate. You don't have to see color change anymore, or whatever the potential is here. So extrapolate, and this is your endpoint volume for calculation. So this is pretty neat stuff. Okay, and that's why named after the guy Graham. Thank you for your attention. See you in the lab.
Question, right there you can CL minus remaining is 0 at endpoint. Are you referring to the molar CL? You have the arrow.
The concentration. Yeah. The extrapolation is down to 0 here.